Okay, so here we are. So today I want to discuss the effects of electron-electron interactions in devices that are floating, not grounded, so that we have a finite charging energy, and we will see that this will result in novel non-local effects. The simplest case is the case when you have just one nanowire, meaning you have just two Majorana bound states, and we couple these to normal leads. So this is like a transistor, normal lead, inside is an island. This island is now a topological superconductor, such a wire, and it has two Majorana bound states, and we ask ourselves, how will the presence of these Majorana bound states affect transport in that setting? And the generalization of that will be to have more than two Majorana states on the island later. That will lead to the topological Kondo effect. So the main motivation here to study Coulomb interaction is to go beyond quantum transport features of this zero bias anomaly type. The reason is that zero bias anomalies you can get from a zillion causes. There are many different mechanisms. I mentioned some of those last time. And so the question is there sort of more an ambiguous signature in quantum transport of these Majorana fermions. Yeah, that's the motivation. And so the Majorana single charge transistor has the central island, and then we have two electrodes of normal metal type, where we can imagine just having the overhanging helical wire parts that are not proximity coupled to a superconductor. And these will be the normal leads that are then tunnel coupled to our Majorana island. So in the central part, we have this nanowire in proximity to a superconductor. It hosts two Majoranas, gamma left and gamma right at the end. And now we will include the charging energy of this central island, because it's a floating island, so it's not grounded, it is finite size. It will have a charging energy in general that scales like 1 over the length of this wire here. We will here discuss the low energy limit. So energy scales, voltages, temperatures well below the proximity-induced gap in this material, such that we can ignore above gap quasi-particles. And for now, I will also assume that there is no direct overlap. This epsilon f should be 0, so that we can have a long wire such that the tunnel matrix element between these two vanishes. But we will come back to the general case later. Okay? So the question is, how can we model such a system? Let's start with the island. On the island, we have two kinds of zero modes. First, we have the Majorana bound states. We can form this non-local F fermion, gamma left plus I gamma right. And it's a zero mode, so it has no kinetic energy. And the parity I gamma left, gamma right is linked to the occupation number of this F fermion, so that's plus or minus 1. Both have zero energy. There's a second zero mode in this game, namely the Cooper pairs. The Cooper pairs are described by a number operator, NC, that counts how many Cooper pairs you have on this island, and it's canonically conjugate to the superconductor's phase, phi. Yeah? So in general, phi is a fluctuating quantity. It's canonically conjugate, so you have this commutator NC with phi equal to minus I. That means, for instance, that e to the minus I phi is an operator that lowers the Cooper pair number by 1 unit. Yeah? So we have no kinetic energy, both are zero modes, they sit at zero energy. The only energy comes from the charging energy in that case, namely, we imagine, because it's a floating system, there's some backgate, so it acts like a capacitor, it has a charging energy, E squared over twice the capacitance. So when you put an electron onto this system, you will have to pay a certain energy related to this charging energy. In typical devices, this is of order 1 milli-electron volt, that's 25 Kelvin. So at the temperatures that people usually use in these experiments, which are well below 1 Kelvin, this is a huge energy scale. And then what you have to do is you count how many particles you have on the island with respect to some gate parameter n sub g. This n sub g you can basically tune by a backgate voltage in a continuous way. And 2nc is the number of electrons in Cooper pairs, and f dagger f is the occupation of this f mode. Yeah, so that's the Hamiltonian. You have to square. It's basically charge relative to some reference charge square. It's a Coulomb interaction of this charging energy type. Because the charging energy is q square over 2c, right? This is the electrostatic energy. So you have to take the charge, square it, and you take it with respect to some reference charge. Yeah. And you see, because of the square, that's essential. If you undo the square, you couple the Majorana dynamics to the dynamics of the Cooper pairs. So you have a handle to sort of access the Majorana dynamics through such effects. The first thing one can immediately notice is the absence of the even-odd effect. It's also called the parity effect in these ultra-small superconductors. This has been studied intensely in the 1990s, and people have shown that the ground state energy or low energy, free energy at low temperatures of such grains of superconductors has an even-odd effect. So that means there is a difference in the ground state if you have 10 to the 23 particles or 10 to the 23 plus 1. It's very amazing. You are in this limit of extremely many particles, and then it depends whether it's even or odd. Why is that? For an n even, you can lock all the particles in Cooper pairs, but for odd number of particles, you have to occupy at least one quasi-particle state. So that will have a gap of order delta, and that can be seen in experiments. Yeah? It's one of the really amazing experiments done in mesoscopic physics in the 1990s. That is the even-odd effect. In the case of Majorana bound states being present, there should not be this even-odd effect, because instead of going to a high-energy quasi-particles, you simply go into this F state. You simply change the parity and occupy this zero mode, and thereby the energy is just basically always zero. Yes, please. This has been attempted, but of course you could also have an accidental zero energy level from some other cause. I mean, Majorana is not essential for that. It's just if there's a subgap state at zero energy, it will also give you the absence of the even-odd effect. But so I would say this is a necessary but not sufficient proof for Majorana. But people are of course trying to see this. Yeah. So to my knowledge, it hasn't been published, but at least some experimentalists tell me that they have seen traces of that. Yeah. Now, if you add, so the prediction is indeed, if you tune, for instance, for our nanowire, you tune the magnetic field to above delta. So to tune the wire parameters into a topological phase, you should remove the even-odd effect. Yeah? That's a necessary but not sufficient detection of Majorana fermions. Now, if you have also the charging energy in the game, then of course different particle numbers will depend in this typical Coulomb parabola fashion on which particle number you have. And that's the modeling of the island. So the island is just this charging energy term. The leads, one can't see it here very well, so there should be leads here that are tunnel coupled to our Majorana states with some hybridization gamma left and gamma right, which are tunnel amplitude squares. So these normal leads we can simply describe as spinless helical wires, because these are the overhanging parts of our nanowire, and they will have basically, these are Fermi gases, yeah? Standard thing. You have Fermi functions here, and the difference in chemical potentials is your applied bias voltage. Now, the electron tunneling we have also discussed in the last lecture. At low energies, we can only tunnel electrons through this Majorana bound state. So in a sense, the Majorana bound state serves as a stepping stone to get into the wire because of this gap inside the wire. So what we did is to project the electron operator in this central portion down to the Majorana sector. And then the tunnel amplitudes here basically contain the Majorana spin structure, the spin structure of the wave function directly. And you arrive in a first guess at such a tunnel Hamiltonian. So we assume here that the source, the left electrode, tunnels only to the left Majorana, and the drain, the right electrode, only to the right. Yeah, they're far away from each other. We have tunnel amplitudes T left and T right, complex numbers. C left annihilates an electron at the contact at the left lead, and likewise for C right. So this is the typical tunnel Hamiltonian. You go from the right lead into the Majorana state or back. That would be the first guess. And the gammas that I mentioned are then related to the absolute squares of these T's, and we can define a line width of the zero mode, this F fermion mode, which is just the sum of these two, gamma left plus gamma right. But now we should be careful, because this version here holds for a grounded wire, and we really have to make sure the charge is conserved. We have a floating device here, so when we tunnel in, we have to make sure that no charges are somewhere lost. Yeah? That's no problem in a grounded device where you can pump in Cooper pairs for free. So in that case, let's re-express the gammas in terms of F and F dagger. Naively, it's F plus F dagger for the left Majorana. And we can now see that we can rescue charge conservation by inserting here e to the minus I phi operator, which removes a Cooper pair. It's a Cooper pair splitting operator, namely C dagger F. That's fine with particle number conservation, but C dagger F dagger would add 2 particles to the total system. And this you cannot do in a floating device, so you have to take these 2 particles by splitting a Cooper pair, which is done by this operator e to the minus I phi, which lowers the Cooper pair number by 1 unit. Yeah? Phi is the order parameter on the island, canonically conjugate to the Cooper pair number. Likewise, on the right-hand side, you also have to insert this part. And after gauge transformation, so using instead the fermion operator F in this form, so you put this phi phase into the definition of F, it looks in a nicer way. So this is then the tunnel Hamiltonian we shall use. We have tunneling on the left or right side with tunnel amplitudes T left right. Electron is taken from the left or right lead and tunnels into the topological superconductor. And this gauge really emphasizes that the gamma is a neutral particle. So it has no charge. The charge is now sitting in this e to the minus I phi half. Yeah, this basically is removing 1 electron charge on the, or adding 1 electron charge on the topological superconductor. Yeah, so in a sense, this is again a fractionalization of charge and spin, so to speak. So with that, we have the model in place and can do computations. The main observable one is interested in is the conductance or higher moments of the current, like noise or cumulance of current fluctuations. And here, for instance, for the current, one can derive the analogous formula known for quantum dots with interactions. This is the Mayer-Wynn-Green formula, which tells you that the current through the left or right contact can be expressed as an integral over energies. Here is the lead distribution function, F, with the chemical potential in the respective lead. F of E is simply 1 minus twice the Fermi function at finite temperature. That's just this hyperbolic tangent. So here the properties of the leads enter, and this quantity here is the spectral function of the island, basically of the Majorana fermion that belongs to this index G. So what you have to compute is the retarded Green's function of this Majorana in the presence of the coupling to the leads and in the presence of the interactions. Yeah? So that might be a formidable task, but once you have this is the spectral function. You just do this integral, you will get the current as a function of voltage. And the differential conductance is then defined as the IDV, where we take the current as I left minus I right, because these currents are oriented to flow into the island. So let's check what happens in the non-interacting case. So if we have no charging energy, if this wire becomes extremely long, then the charging energy can be put to 0. In the non-interacting case, we recover the resonant Andreev reflection scenario. Namely, in that case, the Majorana spectral function is just a Lorentzian peak around 0 energy, and the width of the peak is just set by gamma j, left or right. You plug this into this formula. Let's put t equal to 0, and then it's a simple algebra, and you get this formula which I showed you already in the last lecture. So you get at t equals 0 the nonlinear differential conductance. It's 2 e squared over h. This is this resonant Andreev reflection peak value. Finite voltage suppresses this on a scale related to the hybridization. So it's a Lorentzian zero bias anomaly peak. Important is here that the currents through the left and through the right contact fluctuate completely independently. So they don't see each other because they just flow effectively into ground. And indeed, in this case, EC equal to 0, the superconductor is effectively grounded again. So you need finite EC to really have these charging effects and interesting couplings between left and right. In fact, this decoupling holds for all the cumulants, so for the full counting statistics in this non-interacting case. Yeah? So that's the resonant Andreev reflection scenario in the non-interacting case. Now let's look at what happens in the opposite limit if we have very strong EC. If we have charging energy much, much bigger than gamma and much, much bigger than temperature. In that case, first person to study this was Liang Fu in a very nice paper in 2010. He studied this case of StrongCoulomb blockade at near half integer ng. So this gate parameter, when it's half integer, you are near a conductance peak. And in that case, this strong charging energy allows only 2 basically degenerate charge configurations on the island. Yeah? You have this charging parabola. It will only allow you 2 states, and in that case the model can be mapped to spinless resonant tunneling model, for which it's very well known conductance is E squared over h. It's a spinless resonant tunneling model, so at 0 temperature we have E squared over h, not 2 E squared over h. So there's a halving of the peak conductance as compared to the non-interacting case. Fu interpreted as this phenomenon as teleportation. I would say that's a slight abuse of notation. You have seen Volodya's lecture. Teleportation is really something slightly different. What he meant with that is that an incoming electron that comes in from the normal side Thank you. So that means we expect here a crossover or transition. As we raise EC, we should expect a crossover from this resonant Andreev reflection to the teleportation limit as we increase EC over gamma. Yeah? We have studied this crossover quite in some detail, and let me show you some of these results here. So for WeakCoulomb blockade, so when EC is not too strong, one can use a semi-classical functional integral approach to the phase dynamics and compute the interaction corrections to the conductance. It's analytical and fully controlled, so this limit is under full control. Once you go to strong Coulomb blockade regime, this cannot be used anymore. In that case, you have 3 different ways to describe the situation. One is the master equation. That's also something that Volodya has explained to you. This usually requires the temperature is above this hybridization scale. So in these nanoscopic or the mesoscopic systems, you can only use these master equations at finite temperature. We have done that by including sequential tunneling and all co-tunneling processes, including local and crossed-Andreev reflection, and I will discuss this in a few minutes. I will also discuss this in a bit more detail. These two I will not discuss, just say what it is. Equation of motion approach, this can be developed analytically for the peak conductance near strong coupling, strong charging energy, and then there's a simple toy model, basically a zero bandwidth model for the leads, where you model the leads as single fermion sites, and then you can diagonalize it numerically and plug it into this Mayer-Wingreen formula to get otherwise exact results. So let's briefly address the WeakCoulomb blockade regime, in which, in a sense, the charge fluctuations are still big. EC is small, so it cannot yet pin the charge on the island, so the conjugate phase fluctuations are small. So that means the phase is well defined, and you can do a Gaussian semi-classical expansion around its mean value. In that case, you will not really have a dependence on this gate charge n sub g yet. If you go through the algebra, you will find that these phase fluctuations, the fluctuating phase, will obey a Langevin equation that looks like the Langevin equation of an effective RC circuit. Yeah? And the frequency of that is basically set by 1 over RC, the RC time. And R is related to dissipation, and EC captures the capacitance. So this frequency here follows from a dissipation strength, which we obtained in this form here out of the chemical potentials and the gammas. I should say at higher energy scales, so this is really appropriate at the lowest energy scales, otherwise this damping becomes frequency dependent. So that's really the low frequency limit. And so what this tells you, this is an equation with an inertial term, then a damping term, and finally there's a stochastic force on the right-hand side, as typical in these Langevin equations. That's Gaussian noise, a Gaussian random force with zero mean, and the only non-zero correlator is this correlator given here, which sits in the function k. And this function is too lengthy to quote it here. I just tell you that in equilibrium, the expressions satisfy the fluctuation dissipation theorem as they should. And at temperatures high against the frequency, this just simplifies to T. And then you have the classical FDT. So indeed, this noise and the dissipation are not independent, but they are linked by fluctuation dissipation theorem. And finally, one can compute this, the current voltage relation from this expression that follows from our functional integral. The only interaction effect sits in this last term here. This F was due to the lead distribution functions, and this is the retarded Green's function of the Majoranas in absence of interactions. So the only thing where that enters is here, and this function is just given here. So you have to compute a solution of this Langevin equation for a given noise realization. This gives you this function phi bar. Then you compute the mean deviation and average over all the noise properties. And since this is a square, it's always positive, so it will tend to suppress your current. Some algebra gives you this result here, and with that you can now really do some algebra at zero temperature to compute, for instance, this nonlinear conductance defined here. I take the symmetric system and zero temperature. The non-interacting case for resonant Andreev reflection. At zero voltage, you approach 1 for this quantity, and for EC larger than gamma, you can analytically show that there is now a suppression of the conductance, and it obeys approximately a -1/8 power law with EC. Yeah, that's also against smelling of Ising, and Ising is sort of related to Kitaev chain. So this 1/8 might not be so surprising. So the full behavior is shown here. So this is this linear conductance in dimensionless units. That's the EC equal to 0 limit. So here we are at resonant and wave reflection. Physically, that's a conductance 2e squared over h. Now you crank up EC, and you see it immediately goes down in a smooth fashion. The analytical result holds only for EC larger than gamma, so then you have this minus 1/8 power law. And of course, you cannot use this theory for too strong EC over gamma. Yeah, so what that tells us, there's an interaction-induced suppression of this conductance. The nonlinear conductance shows something similar. So this is this G as a function of V. For 0 EC, you have the zero bias anomaly as predicted by resonant and wave reflection. And now for finite EC, this just moves down. Okay, so now StrongCoulomb blockade. That's beyond this simple semi-classical expansion, because in that case we need winding numbers. Winding numbers in these phase fields phi. I will come back to that when we discuss the Kondo effect. So they capture really dependence on the gate parameter. But a simple approach that I want to describe in a few slides is this master equation, which holds if the energy scales of interest, temperature or voltage, are above the hybridization scale. In that case, the master equation can be more or less rigorously justified from the full functional integral, and it is formulated as a theory for the stationary probabilities P of Q for having Q particles on the island. Q is twice the number of Cooper pairs plus this number F deca F that you occupy the zero mode. Yeah, so P of Q is this probability to have, it's a normalized probability, so if you sum over all Q, P of Q should sum up to 1. These are positive numbers between 0 and 1. And now this master equation tells you if I sit at a given value of Q, I look at P of Q. These are transition probabilities or transition rates for going from Q to some other state Q prime. So I can lower the probability P of Q by exiting to other states Q prime via these transition rates. But I will also get something from all the other states, because from a state Q prime, which is occupied with this probability, I might come in with the rate WQ prime to Q. So the central object we now need are these rates, and these are computed usually in perturbation theory in gamma. So assuming that there is a weak contact between the leads and the island. So in lowest order, you basically have golden rule rates. This is called sequential tunneling. You tunnel from a lead to the island and really occupy the island. Then there are higher order rates. These are co-tunneling and wave reflection rates. And let me briefly describe this. So the sequential tunneling can change Q just by plus or minus 1. There's no other way. You tunnel one electron in or one electron out, so this will change Q by Q plus minus 1. It's proportional to the gamma left or gamma right, depending on whether you come from the left or right side. And then it also depends on the Fermi function in the respective lead, yeah? Whether the particle was occupied or not. And you have to account for energy differences and the chemical potential there. So this E sub Q is just the charging energy you have for Q particles in the island. And this F here is the Fermi function. So that's standard. The next process, sometimes these rates might be very small because there are no states available in the island. Then the next order can come into play. That's elastic co-tunneling. That's a transfer from the left to the right lead by basically just super tunneling through the whole structure. So of course you have elementary tunneling through each contact, but that's sort of a one-way step through the whole thing. It's a fourth order process in tunneling. Doesn't change Q, so it will not enter the master equation. Yeah, there is no rate for changing Q, so it will not show up in the master equation. There is an intermediate virtual excitation of the island, but this doesn't change the stationary probability P of Q. But these elastic co-tunneling rates show up in the current. So once you have the P of Q, you have to feed it into a formula for the current, and there these elastic co-tunneling rates enter. I should also say that usually in normal superconducting systems, elastic co-tunneling tends to be very strongly suppressed by the quasi-particle gap. But here, the Majorana modes, we will see, can yield important elastic co-tunneling contributions. And then finally, you have Andreev reflection rates, which also show up in fourth order. Now, these are processes that change the number of particles on the island by plus or minus 2. So they add a Cooper pair or they remove a Cooper pair on the island. And there are two types of processes. Crossed Andreev reflection means you take from different leads electrons and combine them to a Cooper pair or split them. That's crossed Andreev reflection. Local Andreev reflection just takes both electrons from the same, either the left or the right lead. Yeah? And as example, I just show you the car crossed Andreev reflection rate. It looks like this, so it's a double integral. And you take two electrons with energy E and E prime, and you have to have them occupied. That's why there are Fermi functions in these energy integrals. And then you have to respect energy conservation. So by taking these two on the island, and you change EQ to adding a Cooper pair, so you have to have this energy. So that's just energy conservation. And then there are amplitudes that relate to the order in which you basically go in steps, whether you first come from the left or first from the right. And that's a tricky integral. It really needs regularization, but it has been shown by other people before that this integral is well defined when you do a principal value integral. Okay? So with all that, we can run the machinery and look what comes out. So for instance here, temperature was chosen at 2 gamma, and we look at the linear conductance as predicted from this master equation, and look at function of this NG parameter. Okay, so we start with the non-interacting point. You see there's no dependence on NG. Conductance is about 0.2 E square over H, factor 10 smaller than 2 E square over H. Why is that? It's because we have finite temperature. Yeah, so there's a strong thermal suppression. I should say in the Couwenhoven experiment in Delft, they saw roughly this type of order of magnitude of the conductance, and they had temperature also of this order. So it's really consistent. It's a thermal suppression of resonant Andreev reflection. How many degrees temperature? That depends, of course, on gamma. In the experiment, it was 100 millikelvin or something like that. So the gamma is typically 60 or 50 millikelvin, but this can be tuned. Now, if you increase EC, you first see that the conductance goes down without any NG dependence. Yeah? That's this WeakCoulomb blockade regime that we discussed before with this Langevin equation. So the conductance goes down, but once the the charging energy exceeds this hybridization scale and the temperature, so starting from say 3 or 4 gamma, you see that it starts to develop these oscillations with pronounced peaks at half integer NG and pronounced valleys at near integer NG. And these are the famous Coulomb oscillations. That means in such a valley, the equilibrium charge on this transistor is well defined. Yeah? So you have an integer, a unique charge that the system prefers. If you want to change this by tunneling onto it, you have to pay energy. You have to pay energy of order EC. That's why this conductance is very small. It's not zero because of elastic co-tunneling. So you can virtually occupy it, but you have to exit within a time of order 1 over EC again. So the conductance down here is completely dominated by elastic co-tunneling. On the peak, you have the charge degeneracy. That's this limit that Fu has analyzed. So you have two degenerate charge states. The charging parabolas just intersect at that point, and you can easily tunnel onto the island by occupying the other charge state. Yeah? But we see there is a reduction, and if you closely look, it's exactly a factor 1/2. As predicted by Fu for 0 temperature, this also holds at all temperatures. Always a factor 1/2. So this is this teleportation limit now at finite temperature, if you wish. And we can even get from this master equation analytical results for the valley line shape. in this StrongCoulomb blockade regime. So if EC is big against temperature and gamma, you find this result. Delta here is the deviation from the valley center, so how far you are. And you see this characteristic dependence of gamma square over EC square. That comes from virtual occupation of a higher state in the island. Yeah, so it's finite, but it's typically very small because EC is large against gamma. So that's exactly this line shape here, yeah, down here. I should also say Andreev reflection processes here turn out to be strongly suppressed by Coulomb effects, and in fact that's a general conclusion from our study that once you have Coulomb interaction, it tends to kill resonant Andreev reflection pretty quickly. You can also evaluate the line shape near the conductance peak. In fact, in the strong charging case, we find this line shape where delta is now the deviation from the center of the peak. So if you sit directly on the peak, delta is 0, and this result is just half of what you get when you just compute this conductance in the non-interacting case. Yeah? So we have this halving also at finite temperature. And so we have both a strong thermal suppression of the peak, which is this gamma over T suppression. And on top we have an interaction-induced suppression, which leads to this factor 1/2. And this is shown at 0 temperature here. The full crossover from resonant Andreev reflection here at small EC. From 2e square over h, you go down to e square over h, the teleportation limit, that's at 0 temperature. Blue curve is analytical from this Langevin equation. This is from this equation of motion approach, which becomes exact at large EC. In between, you capture the crossover nicely with this simple toy model, the 0 bandwidth model. And also at finite temperature, you find such a crossover. Then finally, there are some features that you find in the nonlinear conductance that could be interesting to detect these Majorana fermions. Namely, there should be side peaks. Let me discuss these. For instance, at the degeneracy point, Ng is 1/2. So if we start with small EC, we see here the G of V curve is basically a Lorentzian. That's exactly resonant Andreev reflection, dressed with a little bit of Coulomb corrections. But now as we increase EC, we see that, for instance, for strong EC, you get this red curve, so you still have the 0 bias anomaly, but then there pops up a side peak, or at 8 gamma. Yeah? So you need to be in the strong blockade regime. This also happens at other values of this charge parameter. And the origin of this is, so we see these side peaks on resonance at multiples of 4 EC. The origin then is that the chemical potentials become resonant with 2 almost degenerate higher order charge states. And then you get additional sequential tunneling contributions. However, this works only because we have the Majorana bound states, yeah? Because it requires a change of the Cooper pair number, which you can only do by help from the Majorana states. And in a sense, you can say here, without these Majoranas, you will not have these side peaks. And in fact, the precise peak location is also predicted to depend on some details like in-plane magnetic field that could help to identify such peaks. So much about the transistor. So just to summarize this part, Coulomb charging effects couple the Majorana and the Cooper pair dynamics. We have up to now discussed the simplest case with just 2 Majorana states. That's the single charge transistor, in which one has this interplay or crossover from resonant Andreev reflection to teleportation. And this teleportation would be an example for a non-locality. So in the resonant Andreev reflection, everything is local because the current is immediately sucked into ground. And you don't really see the non-locality that should be inherent in these Majorana fermions. So with the help of the Coulomb interaction, we now see we get a truly non-local phenomenon like this teleportation. And an even more spectacular non-local phenomenon will be this topological Kondo effect, which happens if you have more than 2 Majorana bound states on a floating superconductor. And we will see that in that case, this island hosts a ground state degeneracy, an exact zero mode basically, that can be thought of as a quantum impurity spin that is non-locally encoded by these Majorana bound states. And when you now couple these Majorana bound states to normal leads, this spin has an exchange coupling, like a normal spin exchange couples to conduction electron spins in metals that then induces a Kondo effect. So we get an equivalent Kondo effect now for this strange quantum impurity spin. This has been called topological Kondo effect because this quantum impurity spin is built from Majorana bound states. In that sense, it's topological. Yeah? And in fact, such a Kondo effect is predicted to be of multi-channel type, non-Fermi liquid character. It is predicted to be stable, unlike typical two-channel Kondo proposals that always suffer from the problem that anisotropies are relevant perturbations and can easily destroy the fixed point. This problem here will be intrinsically stable and can be observed in electric conductance measurements. Yeah? And attempts are underway in the Charlie Marcus lab to see this at the moment. So the history was basically Berry and Cooper first pointed out that this quantum impurity spin can exhibit such a Kondo effect. We, with Alex Altland and in a collaboration with Alexei Zvelik and Benjamin Berry, then also worked on understanding this type of effect. This is the paper that I told you where you can find all the details. And in fact, I think all of the authors of this recent Nuclear Physics B are in the room. Francesco Buccari, Professor Babushian, Professor Koreppin, Professor Sodano, and Professor Trompetoni. So it's a topic that is increasingly arising interest. So what do I mean with the spin? So let's consider the following picture. So this box here is a superconducting island, and we deposit now, for instance, here 3 nanowires. Let's say n larger than 1 helical wires. So these parts here will be topological superconductors. They host Majorana bound states at their ends. Yeah, so in that case, we would have 6 Majorana bound states on this island. And now parts of these will be overhanging. Yeah, so for instance, this would be overhanging parts that we can use as normal leads that are tunnel coupled here at these contacts. So in general, we will have m less or equal than 2n Majorana states on this island that are tunnel coupled to leads. Yeah, so m is the number of Majoranas that are tunnel coupled to their own leads. And the leads we can model as Luttinger liquid wires with G less than 1, G equal to less or equal than 1. Luttinger liquid is a generalization of this helical Fermi gas to include Coulomb interactions. So this I do because we can do it for free with the method that I will sketch in what follows. This G parameter is equal to 1 if you have no interactions, so the Fermi gas you just get back by putting G equal to 1. With repulsive Coulomb interactions, G is less than 1. So the central role will of course now be played by the charging energy. So we assume a strong charging energy on the island, and we assume that this gate parameter Ng is nearly integer. So we have a unique equilibrium state on the island. Higher charge states, other charge states cost you an energy at least of order EC. Yeah? So there is a well-defined unique equilibrium charge state. But now we have a degeneracy on this island because out of these two we can form a fermion, these two can form a fermion, and so on. So for n wires we have degeneracy 2 to the n. For each one we can either occupy or not occupy the fermion, degeneracy 2, 2, 2. So there will in general be a 2 to the n-fold degeneracy, but we have to respect a parity constraint because of this fact that the charge state is uniquely defined. This I will explain on the next transparency that reduces this by a factor of 2. So in general, for n wires, you have a 2 to the n minus fold ground state degeneracy because of these Majorana states. That's the central issue here. That really encodes this quantum impurity spin. So in the minimal case, just 2 wires. We have 4 Majoranas, and we can form a 2-fold ground state degeneracy. This will be like a spin 1/2. But this spin 1/2 is built in a weird way out of 4 Majorana fermions. Yeah? And this spin 1/2 degree of freedom that is sitting on this island will now couple to leads. Yeah? So that is the setting that we have here. And you see directly for the transistor, this will not work because the transistor was n equal 1. There's no degeneracy in that case. The charge is unique, fixed, and then also the Majorana parity is fixed. As long as temperature stays small enough, of course, this will all persist. But for now, I'm just looking at very low temperatures compared to the charging energy so that you cannot really occupy higher charge states. So different from the one that minimizes the Coulomb energy. Yeah? So you have a Coulomb energy. Let me just write this. So we have this Coulomb energy EC and now this NG I choose integer, let's say 0, so we can get rid of it. So it's just Q square. So that will mean Q equals 0 is the minimum, and to have Q equal plus minus 1 you already have to pay the charging energy. As long as all energy scales are well below the charging energy, these can only be virtual processes. So in fact, the charge, as shown here, twice the number of Cooper pairs plus the occupation number of all these F fermions that you can form. Alpha is now a wire index. You go from index 1 to n. For each of the wires alpha, you form the Majorana combinations, and then these are 0 or 1. Yeah? And this must be constant, in that case 0, or if ng is 1 or odd, it's some other integer number. Yeah? So that means that the degeneracy of the Majorana sector a priori is 2 to the n, because here you have 2 to the n ways of distributing 0 and 1 in these F decker F. But now we have this constraint, namely we need to have this, if the constant is odd, then also this here needs to be an odd number. If this is even, also this needs to be an even number. That's a parity constraint, and this parity constraint transfers back in the Majorana language into a constraint of this type. The product over all the Majoranas needs to be either plus 1 if this is an even number, or minus 1 if this is an odd number. So there's a parity constraint on the allowed states in this Hilbert space. Yeah? And that means the degeneracy is 2 to the n minus 1. Okay? For now, I will neglect all the Majorana overlaps by assuming that the wires here are long and far from each other. Yeah? That's the simplest case, in which case we can make considerable analytical progress, and I can show you nice results. But in the end, I will also show you what happens when you allow for generalization. Okay, now let's discuss the leads. In the leads, we have one-dimensional spinless helical liquids. So the leads basically are one-dimensional systems, and we label them by 1 to m, and they are described by left or right-moving Dirac fermions. Yeah, so we take here a geometry. For instance, here's this island. I pick out one Majorana, for instance, gamma j, and now here we have this wire, and this is our coordinate x. At x equal to 0, we place the contact, And it's taken as semi-infinite, which means we have now a right mover, psi j right of x, and we have a left mover, psi j left of x. Question is now what happens at this point x equal to 0. Since we connected to the island by tunneling, we impose the boundary condition that each right mover is reflected into a left mover, or the other way, each left mover into a right mover. So they match each other up to a phase that is irrelevant at x equals 0. Yeah? So that's our boundary condition here. And the low energy Hamiltonian then looks like this. You have right movers, so the Hamiltonian for a right moving Dirac fermion is minus I psi dagger dx psi. For the left mover you have a minus sign here. Okay? I use units with h bar and Vf equal to 1. There might be electron-electron interaction terms, which I don't write out here, so that's just the kinetic energy. And you can also use an unfolded picture that's very often used by saying that instead of using a left mover and a right mover, I can only use a right mover along the full line by basically folding this to negative x. Yeah, so the definition is that a psi left of x, this psi left of x is taken as psi right at minus x. Oops. With this, you automatically fulfill the boundary condition, and then you have just a single right mover, but on the full line. Yeah, so that's the standard unfolding procedure. Sometimes this is more convenient. Okay, now the next step is to invoke abelian bosonization. So that's a method that's well known in the theory of one-dimensional interacting electrons or bosons. It offers us here a very convenient description of the topological Kondo effect, even if there are no interactions in the leads. Interactions in the leads, so this G parameter, Lattinger liquid, you can treat for free using this method, so that's why I included them. And in that framework, in bosonization, you represent the lead fermions, so these operators psi j right or psi j left, in terms of a dual pair of boson fields. So the central quantity is given here, so that's this bosonization identity, which we write down. It is written as a so-called Klein factor, and then the important thing is a phase exponential. So you write it as a phase field phi j of x plus or minus a second phase field theta j. These phase fields are bosonic in nature. That's why it's called bosonization. You express your fermionic fields in terms of bosonic fields. And these boson fields here are defined for each wire, j, j prime, and they have this algebra here. So that means phi is canonically conjugate to dx theta. In fact, the physical interpretation of dx theta is the charge density, which is why I will call the theta field a charge field, and this is a phase field that's canonically conjugate. Okay? And now, because of this commutation relation, you can check that this formula satisfies anticommutator relations in a given lead. So if you do an exchange of electrons in a given lead, you will indeed find the correct anticommutation rules. It's all hidden in this algebra here. But if you want to have anticommutation rules between different wires, this is not done by these. So for that, one adds these Klein factors to make sure that different wire electrons also anticommute, and also that these fermions anticommute with the Majoranas that we have on the island. So these are have to obey a Clifford algebra and should obey this. And the simplest way to satisfy that is simply to take them again as Majorana fermions. So we have now Majorana fermions or bound states attached to these phase exponentials. So that's a new set of Majorana fermions defined for each lead. And that turns out to be very convenient when we come to the tunneling. Yeah? But let's first discuss the lead Hamiltonian, so this Dirac Hamiltonian that we just had here. Such a Dirac Hamiltonian, or this one, can be expressed in terms of the boson fields, and that's a well-known story. Maybe Giuseppe will expand a bit on that. It's a Gaussian theory, so it's basically the Hamiltonian is just the sum of dx theta square and dx phi square. So that's the canonical momentum to this field, and here we have this Latinger parameter G entering, so I will consider here the weakly repulsive case of equivalent to a spinless Latinger liquid. G equal 1 gives you back the Fermi gas. Yeah, so the leads are simply a Gaussian theory in these bosonic phase fields, so we can use whatever we want. It's quadratic, we can integrate them out later. And the important point is now that we have, in terms of these phase fields, Dirichlet boundary conditions for the charge fields. Yeah, we start here from 0, go to infinity. 0 is the boundary. Why do we have Dirichlet conditions for the charge fields? It's because we want to have this boundary condition. And now if you look here, the right-left comes with a different sign. So if both match, we should pin this field theta. Yeah, so the theta field will be pinned, meaning it has boundary conditions of Dirichlet type at x equal to 0. On the other hand, the dual field, which is the phase field, must then have Neumann conditions. Yeah? So we have Dirichlet conditions for the charge field, Neumann condition for the phase field. And now comes the benefit of using bosonization in this game. So let's look again at the tunneling Hamiltonian. Yeah? That's the tunneling Hamiltonian I discussed in the transistor. And now we simply have J running not over left and right, but from 1 to m. There's a tunneling amplitude for the jth contact. This is now the fermion operator at the contact. You create an electron in the jth lead at the contact, and at the same time you have to take out the charge, e to the minus I phi half, extracts one charge out of the island, and you come out from the Majorana. Okay, that's our tunneling Hamiltonian. And now we insert our bosonized expression that you have here for x equal to 0. Right and left are equal. So this will be eta j e to the I phi j of 0. Okay? So you insert this into this tunnel Hamiltonian, and what you see is you get here there is a eta now. You have a gamma. There is a e to the minus I phi half. From this one you have a e to the minus I phi j of 0. And then adding the Hermitian conjugate, this is what you get. You get a sine of phi j of 0 shifted by phi half. And you have here this product, it's a parity product of the Majoranas, eta and gamma. Who? Der anti-commute. Yeah. Okay? And that's very interesting because now we see that the Majorana fermions, they only appear in these combinations, and that means they are all conserved. All these parities are conserved. In other words, we can fuse this Klein Majorana, this eta, and the true Majorana at each contact. So we form a new fermion, dj, like this, and d dagger d, 0 or 1, is given by that. So this parity is just conserved. And in fact, you can gauge it away. This is plus or minus 1. You can eliminate the minus 1 by shifting phi j by pi. You just do a phase shift. Has no physical effect, and you can gauge it away. That means the complete fermionic sector of the theory is solved instantly by this trick. Yeah? You are left with a bosonic problem only, and that's a dramatic simplification. For instance, people working in this business of Latinger liquid junctions, Y junctions, or junctions of many Latinger liquids meeting at some point, they know how complicated this problem is, because you have to take care of this Majorana eta field dynamics. It's a horribly complicated problem here. It's much simpler because of this simplification here. So the next step is as follows, and then we are almost done for this morning. So we now can integrate out all the boson fields away from the contact, and in the second step also we can integrate out the phase field phi on the island to express everything in terms of these variables. Phi j, these are the boson fields, these fields here in the jth lead at the contact. Okay, so the thing is that you write down the partition function as Euclidean functional integral over this field phi. That's our superconducting order parameter. Because of the charging energy, it has a piece in the action that looks like this. Tau here is the imaginary time, and it's sensitive to phi dot square. And then we have a functional integral over all these boson fields, and the effective action looks like this. Here, that's the tunneling from Leeds to the Majorana island. This was our Hamiltonian. I told you can gauge away this piece, so you are just left with Tj times the sine of phi j plus phi half. And you integrate, as usual, in a Euclidean path integral. The time goes from 0 to h bar beta, so 1 over temperature. Yeah? So this describes tunneling. The effect of integrating over the Gaussian Luttinger liquid modes away from x equal to 0 is to give you this first part. It gives you a ohmic dissipation-like kernel. So here I switch to frequency or Matsubara frequencies. And this linear frequency dependence means it's ohmic dissipation. Standard, the dissipation strength is set by this parameter G here, so that comes from excitations in the leads. In the leads you have gapless excitations, electron-hole pairs, that will damp the dynamics of these boson fields. Yeah, so there is one complication here that people often tend to forget, namely these fields phi here obey boundary conditions of this type, they can wind. So by going once around, I mean the Euclidean time has topology of a ring. By going once around the ring at 1 over t, you have to sort of, you must allow for windings of this type. W is an integer number, and it can wind in our units by 4 pi. However, and you see these winding numbers here eventually are the only thing that couple to Ng. Yeah? However, near Coulomb Valley, and that's the situation we are interested in here, in this topological Kondo effect, you can show that only effectively the 0 winding number contributes. So that's a subtle issue, but that can be sorted out, and from now on we will just stick to the 0 winding number sector, and we can forget this here. Okay, so 1 or 2 more technical steps, and then we are at the final action with which we can really discuss this topological Kondo effect. So now, as you see here, we have in the nonlinearity this combination phi j plus phi half. We can remove this by shifting all the phi fields such that we get rid of this in the nonlinearity. So the phi field is thereby gauged away in the tunneling term. But then, of course, you get a term phi plus phi or minus phi half here, so that will generate a phi square and a mixed term. But you see now the total action for the phi is Gaussian. Means you can also integrate it out, and therefore you end up with this action which is only a function, so it's a partition function written as a functional integral only over these m phi j fields with an action that's written here. The tunneling looks now just like sine phi j. And now we see that here the EC term really affects only one specific linear combination, namely this q equals 0, 1. So this phi tilde with q equals 0 is just 1 over square root m phi 1 plus phi m. So that's why one switches here to different linear combinations of our phase fields to express this term after the integration. Only for q equal to 0, only for this special linear combination, EC is active at all. And that's clear because EC locks the total charge, and that means the conjugate total phase, which is this sum, is basically freely fluctuating. So on energy scales, omega below EC, this is very big, and you see it scales like omega square. It's a free action. So the phase fluctuations of this total phase are huge. So it is a hugely fluctuating phase, and that reflects precisely the pinning of the conjugate charge degree of freedom. And that's precisely the physics we are after here. Yeah? All the other linear combinations that you could form here from Q runs from 0 to m-1, so the remaining m-1 linear combinations are not affected by that, so here you still have the standard ohmic damping. So this is now a nice starting point to run a renormalization group analysis. Namely, you can discuss this bosonic action in the framework of the RG technique. So you start with some high energy cutoff, integrate away a small shell, and look how parameters adjust to accommodate the integrated out modes. If you do this at very high energy scales above EC, these charging effects you can simply forget. Yeah? They're irrelevant, and what you find then, you can forget this, and the effect is then that all these tunneling amplitudes renormalize completely independently. So they don't see each other, and they renormalize upwards. So by going down with energy scales, they go up in a power law fashion as given here. Physics is this is the RG flow towards resonant Andreev reflection. Yeah? As expected, all the TJ are independent, and they move towards resonant Andreev reflection. But at energies below EC, we get that this mode here becomes free, fully fluctuates, and in that case, the charging effects induce a confinement. So we can make a nice analogy to QCD. In that case, the particles are in-tunneling events. You come from some lead J, go into the island. The out-tunneling events are the antiparticles, in a sense. And because this is strongly fluctuating, you can only sit on the island on a time scale of order 1 over EC. You have to get out after that time scale, otherwise you have to go into this excited charge state. So in a sense, you have to co-tunnel through this dot. You have to go from lead J to lead K, and thereby these in and out tunneling events form bound dipoles. Yeah? They have a coupling that's given here, Tj times Tk for the individual tunnel processes, and then there is a 1 over EC denominator because of the finite time they can spend on the island. And just notice here these bare values for the couplings of these dipoles. They scale like such that for small EC, these couplings are large. I will use this later. Yeah? And then on energy scales below EC, these dipoles are really the good elements of the theory. You cannot sort of break these dipoles anymore. And in fact, this QCD analogy is explained here again. So we have this phase field mode, which is free at energies below the charging energies. Charging energy, it's conjugate to the pinned island charge, and therefore it fluctuates very strongly. It enforces a finite lifetime of excited island states. So in and out tunneling events can be separated at most by times of disorder. And we say the particles or quarks are the intunneling events, antiparticles are antiquarks are the out-tunneling events, and now particles and antiparticles bind together, so these are dipoles or mesons at low frequencies or energy, that's confinement, while at high energies they are basically free. So this looks like asymptotic freedom. And in the following I will just stay on low energy scales well below EC, where the action effectively becomes like this. The dipoles are now locked together, so you have e to the I phi j must be followed by e to the minus I phi k. E to the I phi j describes tunneling into the dot from lead j. E to the minus I phi k means tunneling out from the dot into lead k. And here we have these couplings lambda jk that describe the amplitude for co-tunneling from lead j to lead k. Okay? And effectively we have now ohmic dissipation. EC doesn't appear here anymore except in the bare values of these lambdas, and it sets the cutoff for our theory. And that's a nice action now, because we can say this looks like a quantum Brownian motion picture. Imagine we have a particle with coordinates phi 1 to phi m in some m-dimensional space. This particle is subject to dissipation, ohmic dissipation, so it is a damped particle, and it moves in a periodic potential of this type. Yeah? So this is actually a hypertriangular lattice, so we can later exploit this analogy to quantum Brownian motion to extract information about this system. The first thing you would do now is to run the standard renormalization group procedure. So on the one loop level, these are your RG equations. There's a first term that comes from basically a suppression by the Luttinger tunneling density of states. So that is a term that tends to decrease these couplings. And then there's a second term that tends to increase these terms that comes from dipole fusion processes. Namely, two such dipoles, when they come close, they can fuse to just one. It's similar to this operator product expansion that Giuseppe was explaining you. Two operators basically fuse to give one, and that is basically described by this process. Yeah? So we have two competing tendencies, which means there is a fixed point in between. There's an intermediate fixed point that is isotropic, so all the lambda jk are equal to some lambda star given by that. This requires more than two leads, but once that's there, you will have this intermediate fixed point, and that's an unstable fixed point. The diagonal elements of this are zero. They're just zero. So you only get something if m must be different from j and different from k. So that means when m is yes, yes. Exactly. It goes towards isotropy. Exactly. The flow will be towards isotropy. That will come basically as last thing of this lecture. So I showed you these RG equations allow an unstable intermediate fixed point, but they also have two stable fixed points. One trivial one you can directly see, lambda equal to 0. So if you completely decouple this island from all the leads, you don't get any transport, then that's a stable fixed point. The other stable fixed point would correspond to letting these go to strong coupling, and that will lead to the Kondo effect. So we expect here two stable fixed points, namely 0 and infinity. Which one wins depends now on whether the initial typical value of the initial coupling is bigger or smaller than this critical coupling here. So than this intermediate fixed point. Yeah? If you're to the right of the intermediate fixed point, you will flow to strong coupling. If you're to the left, you flow to weak coupling. And this ratio is now given here, so one sees that for not too strong EC, you will always flow to strong coupling. So for the other case, the insulating junction, you get the usual Luttinger liquid physics, power law, suppression of the conductance matrix. The other limit is exactly this flow to an exotic non-Fermi liquid Kondo regime. In any case, in both cases, resonant Andreev reflection is always unstable. Yeah? It's always killed in both of these limits. So here we are only interested now in the case that these lambdas initially are bigger than this fixed point value. This will always happen if there are no interactions in the leads. Then you're automatically in this region because then this lambda star is 0. So for non-interacting leads, you will always flow into this topological Kondo regime. If there are interaction in the leads, you need a finite or not too strong charging energy. And this plot here shows you the numerical integration of these RG equations, and it shows that you indeed flow to strong coupling, and you flow so in an isotropic way. So it's a flow towards isotropic couplings. All the anisotropies in this flow can be shown analytically are RG irrelevant. So this sort of self-stabilizes itself towards an isotropic flow, and that will imply the stability of our Kondo fixed point in the end, yeah? Because anisotropies are just irrelevant. That's unlike the other known, to me at least, realizations or proposals of multi-channel Kondo physics. So that indicates that we flow to some strong coupling limit, but of course perturbative RG is not able to tell you what this strong coupling limit is about. Indeed, the perturbative couplings diverge at a certain energy called the Kondo temperature. You can estimate it like here. And then you have to switch to some other scheme. And in fact, in that case, this is what I will discuss in the next lecture. You will go to the strong coupling limit of this topological Kondo effect. But I guess it's probably a better idea to stop at that point and leave this for the afternoon lecture, where we then discuss really the topological Kondo effect and what happens near the strong coupling fixed point. So with that, I thank you for your attention.